Hello everyone, this is Bolin speaking. A couple of people have asked me if I can help them out with optimization since this is pretty much a new topic that a lot of people are facing. So I thought it might be a good idea for me to make a video similar to what Dr. Labar did for our summer courses, and so that everyone who may be in a similar boat can benefit. Now, Dr. Somerville has kindly shed some light on what the exam is about, and specifically she said we're going to have to be taking a problem and using one of the formulation methods we did to solve the problem. Specifically, even more specifically, we're going to have to do a simple formulation as well as a summation formulation, which if you don't remember what they are, I'll talk about them in detail, and probably take the formulation, code it up in SAS, and submit the final results. Fortunately, we won't be covering any of the conceptual problem like duality or shadow prices. So that's great because I have no idea how to do those either. However, I think I have a pretty good grasp on the different type of formulations that we'll be looking at. So I'm going to take some time today to go over all four of them, applying them to a very simple and highly hypothetical problem. Alright, before we begin, apologize for the probably loud and static fan going around in the background. I can't seem to get rid of it. Now, without further ado, let's dive into linear optimization. This is the foundation of all of the optimization techniques we will be discussing, so it's pretty important for you to understand exactly how to formulate this one. Let's look at a problem that I just wrote up, completely fictitious, highly hypothetical. Suppose you're an IA student and there are two exams coming up on Wednesday. Let's give them generic names such as ML and OP. Since you take your study very seriously, you've decided to dedicate a weekend to prepare for the two courses. Now the good news is you're a brilliant student and you're very good at approximating how long you need to prepare. The bad news, you haven't had much exposure to the two courses before. So you sat down and pondered what happened. What would have happened if you were just to write the exam without any preparation? Since you love ML and always paid attention in class, you believe you should get about 80 in the course, no problem. OP, on the other hand, is completely foreign to you. Never had any of this in undergrad, so kind of having a difficulty grasping the concept. And you decided the best you can do without studying is probably a pass, 50. Fortunately, you are good at estimating what you need to do. Since you already know so much about ML, you decided each additional point grade probably is going to require a lot more work, so an hour of studying is only going to give you 2 points. However, each hour spent on OP will probably net you 5 points because, to be fair, you really just haven't had much exposure to the topic. Now, we know this is probably not linear in the real world, but let's assume it is for the sake of this problem. So you looked at your schedule and you have just about 16 hours over the weekend, 8 hours a day, pretty fair. And so it would be pretty hard to get 100 on both exams. Of course, we can't get anything over 100 on the exam. So you decide to optimize the study process and see what's the maximum combined grade you could possibly achieve. Now, how would I approach this problem? As I'm reading it, I will start thinking about the different decisions I can make, as well as keep a tab on the different numbers. Very first thing, we saw we have two exams, ML and OP, to study for. These are generally going to be sets that we have to make decision on. I'll talk more about that after. And as we go through it, we pick up numbers that we should keep track of. For example, without studying, we will be able to get a base grade of 80 in ML and 50 in OP. As well as each hour of studying will net us 2 points in ML and 5 points in OP. And finally, other numbers, such as our total time studying cannot exceed 16, and then our grades probably won't be able to exceed 100. So given this, it becomes a little more obvious that we're trying to make a decision about how to allocate the 16 hours among these two courses so that our maximum combined grade is optimized. And there you go, that's almost our formulation. Unfortunately, we have to write them down in a more mathematically rigorous manner. So let's start by following the different steps that we've taken in this course. We began by identifying sets. Now the concept of set might be new to some of you who haven't had rigorous training in mathematics. As a business student myself, how I approach this is thinking of sets as primary keys. In this particular example, we have two primary keys, ML and OP, probably strings, that can be used to look up value within the inputs or your decisions. Now, we saw in our project that these keys don't have to be just one field. We could have, for example, region by product, which is going to give us the number of region times the number of product, different composite keys. But I digress. So using this primary key, you could look up value of the inputs that we're going to be talking about. For example, our base grade. If I tell you use OP to look up base grade, you are going to tell me the base grade is 50. This corresponds to the base grade with subscript OP and having a value of 50. So again, sets, I think of them as unique primary keys and the inputs as value corresponding to those primary keys. So let's draw our table. Grades per hour, we have 2 and 5. And finally, we have total time less or equal to 16 and max grade equals 100. So the decision then, as we talked about, is the number of hours you want to study this weekend on course C. And let's denote that as hour under subscript C. So let's think for a second, what does hour subscript C mean? It means for each element C in the set course, which corresponds to ML and OP, I am making a decision about the number of hours to study for that course. So there are technically two unique variables that we're going to be looking at. If there are 100 courses in my set course, then we'll be creating 100 variables here. So that's kind of the concept of sets, inputs, and decision variables. Now, once these are defined, we can talk about the formulation itself. For this exam, we're going to have to do both a simple formulation and a summation formulation. A simple formulation is one where we explicitly kind of write everything out. You probably heard a loud buzz there, sorry. Whereas the summation formulation is probably what you remember from the optimization homework involving all these signs and variable names. As you will see, for a small problem like this, simple formulation is very easy to write, very easy to implement. But as the problem grows, you're going to have to really leverage the summation formulation. And again, as an example, in our homework, it would be pretty much impossible to write it out using a simple formulation. So, what is the simple way to formulate this? We wanted to maximize grades, and what is grade? The grade is simply the summation between your grade in ML and your grade in OP. Your grade in ML is given by the base 80 plus 2 times the amount of hours you want to spend. Your grade in OP is the base 50 plus 5 times the amount of hours you want to spend. So you would like to maximize this, but you have constraints. Specifically, the amount of grades in each course cannot be over 100. And the total hours you're studying cannot be greater than 16. And finally, you should not be having negative hours. Now, some of these may be redundant. Specifically, I think the hour greater than 0 constraint might be redundant since it's probably bounded. But don't worry about those. These are constraints that make sense to write. And, let's start writing these logically. So, the more useful way of thinking about larger problem is formulation using summation. So, these should technically correspond to each other on one-to-one basis. Again, we're maximizing a variable called grade, which is calculated by base corresponding to the course we're studying, the number of hours we're studying for course C, multiplied by the grades per hour gained in the course C, summed over all courses. In this course, we have C equals ML, C equals ML, and C equals OP. So if we really expand this out, we're going to get base ML plus hour ML multiplied by grade per hour ML plus base OP plus hour OP multiplied by grade per hour OP, which is exactly what we had here. So as you can see, the summation formulation is really just a compact way of writing the problem, which is really beneficial when we start having larger and larger problems. So very quickly, how do we write other constraints? These two constraints are kind of similar in that it's saying your grade must be less or equal to 100 for all different grades, right? If you're not familiar with the for all sign, that just says every single one. So we can write it like this: your base grade for the given course C plus your hour for the given course C multiplied by the grade per hour for the given course C, which as we saw is your final grade, must be less or equal to the course max, which is a constant 100 for all C in course. This, in English, this says for every course, the grade you achieve has to be lower than the maximum grade. Similarly, we can look at this one. If we sum over all courses, number of hours we're spending, what does that give you? Well, that gives you the total amount of time you're studying. This has to be less or equal to total time. Now, we don't have to do any type of indices because we're looking at everything in aggregate. Finally, our constraint greater than 0. So we cannot really spend negative time on each course. So again, for all C in course, or for every course out there, the number of hours you spend studying on that course have to be greater than 0. So this is our formulation. And we're going to talk about how to program this in SAS. Now, since we're doing this dog-leg bar style, to SAS we go. That is our homework, which we will not be using. Let's start by creating the data set that we're going to be looking at. Very easy using a data step. We're going to create a very small table called linear problem, where in the seed where we have the column variable course, base grade, grades per hour, grades per block, which will be used later on. Don't worry about this for now. And course max. And here's the values that we saw earlier. So it's important to remember that proc-opt model almost corresponds with your formulation on a one-to-one basis. So we saw with our formulation, we have a set section, we have an input section, we have a decision section. This is not going to be really in there because that's just a different way of writing formulation. And then we have the formulation itself. Your proc-opt model is also going to have every single one of these. Let's start by the set. Our set was something called course, which takes value ML and OP. So we create a set in the seed on string called course. And we read in data from the problem we created, linear problem, and we read the value in the column course. It's right here. Wait, sorry, this one. We read this course corresponding here and store them in our set, which is here. This creates our set that we're going to be using to index every single inputs. Next section then is our inputs. We're creating 3 inputs here: the base, denoted by indexed by course, the grades per hour indexed by course, and the maximum grades indexed by course. We can combine this in one single line of input in SAS. So again, we read the linear problem data, and this is kind of the syntax. Indexed on course, which corresponds here, and here, we're going to store the value in column base in your numeric variable base. We're going to store the value from grade per hour column in your old table into our numerical set or numerical data value variables called grade per hour, which corresponds here. So whatever is after equation's equal sign corresponds to the column name of your data source, and whatever is before the equation sign corresponds to the name of your set. They both have to be indexed on the same thing. Finally, we're just going to create a total time equal to 16 to denote study time. We probably could have done the same with the course max, but I just wanted to demonstrate you can do this in either way. So here's our decision variable using the var statement. Our number of hours spent on each course is indexed by course. And right now we can calculate an impvar, which is the grade that you will achieve in a given course. And this is an impvar because it depends on our decision variable. So the grade in course C, here is kind of the notation for it. This reads, for every C in course, which in English says for every course. We are assigning the value base C, grade multiplied by hour C, into grade per hour multiplied by hour, sorry, into an implicit variable called grades, which again, as we saw earlier, is indexed on C. And now when we look at writing our objective function, it becomes really easy. Well, what are you trying to do? You're trying to maximize the grade, which is simply the sum of all of these implicit grades. So if we look back at our formulation, this is kind of our grades, which depending on C. And we're trying to maximize the sum over C of all grades variables. Let's look at the constraints. Our first constraint is the grades in a given course have to be lower or equal to max. So for every course in C, the grades we achieve has to be lower than the maximum of the course. Again, this probably doesn't need to be indexed on C, but second constraint, the total amount of hours you're spending has to be lesser than the total time, which the sum of all courses, sum of the hours in every single course have to be lesser than total time. Notice the subtle distinction here. This counting over the set course happens before the colon for the perfect variable, because we want to say for every course we need to make sure this happens. In this case, we're technically creating 2 different lines of linear constraints, one for every course. In this case, our summation happens after the colon, and it really is part of the sum statement. We are creating only one linear constraint that says sum up all your hours has to be lower or equal to 16. And we don't really have to implement the greater or equal to 0 sign because we're trying to maximize this, but it couldn't hurt. So let's write it. Constraint non-zero. Nope. The amount of hours you spend on C has to be greater to 0. So again, what does this say? This says for every course you have to spend a positive hour studying or non-negative hour studying. And that wraps up our formulation. I know it's a little messy, so I will probably send the document out erasing all the comments in it. We can start running it. Select our model, go to the little guy, and we have our solution. So the maximum grade you could possibly achieve is 192 between the two courses, given the constraints we set up. And we recommend you spend most of the time studying for OP, because you can learn a lot in a given hour, and spend the rest time studying for ML. Obviously, with this really simple problem, we could have easily done it without utilizing optimization. But as we'll see in later problems, that this technique becomes a lot more useful. I spent a lot of time on this one because linear programming is probably the most important to get done. So hopefully you understood everything, and if not, just feel free to talk to me. I'll be happy to explain any of the concepts. So now I will move on to the other type of problems. Part 2 of our study deals with integer optimization. Quick overview. Integer optimization are simply linear optimization with additional constraints that your constraint or your objective function or the decision variables have to take on integer values. A commonly used case of the example of this is actually binary programming, which is what I'm going to be talking about. But we've seen some application of using just integer constraints in class as well. These are, as Dr. Samuel suggested, very, very commonly used because most of the problems we face in life are probably integer problems. We have to decide whether or not we're going to do something, for example, or how many of something we're going to do. So let's dive into the problem. Again, highly hypothetical problem. Suppose you're an IA student and you have 2 exams coming up on Wednesday. Hey, I just read this. Okay, let's see what's different. We have our 2 exams, ML and OP, and we have our base grades 80 and 50. This weekend, you can find just 3 blocks of time to yourself. Saturday morning, Saturday afternoon, and Sunday afternoon, for those who go to church. And each block of time that is devoted to studying ML will net you 10 points increase in grade, while each block of time dedicated to OP will net you 20-point increase in that exam. So how is this different from linear programming? Well, no longer can we make a decision about how many hours, maybe decimal, to spend on each course. But rather, we have for each course, 3 decisions to make. Or let's think of it this way. We have 3 blocks of time, and for each time we have to make a decision on whether I'm going to dedicate that time to studying ML or studying OP. So really your decision is over 6 variables, where you can make decisions like this. Whoops. SM, SA, well, that system didn't work out very well. Sat M, Sat A, and Sum A. So for each of these times, we can choose whether we take ML or OP. That's just everything that changes it from the previous linear program to the integer program. Again, not very difficult, right? So let's use the same techniques we talked about in the previous problem. First of all, we go through it and look at the decision that we have to make. We have, again, opportunity to make decisions over 6 variables. Specifically, as Saturday morning, we're going to look at if we're going to study for ML, if we're going to study for OP, and the same for Saturday afternoon and Sunday afternoon. So this creates two sets where we can count our decisions in. Again, we have our C in course, ML and OP, and we're creating a new set called block that contains the value Saturday morning, Saturday afternoon, and Sunday afternoon. And our inputs doesn't really change too much. Base C are the base grades. Grades per block, which if you remember from the SAS code, is 10 and 20. Again, this depends only on the course that you choose to study. Maximum grade as always. So the only thing that really changes between these two problems is our decision variables. Our decision variable now takes on this form. Study block, which is denoted by CB, is equal to 1, so it's a binary variable now, if we decided to study course C for block B, and 0 otherwise. And our simple formulation is, you see this is starting to get complicated, and that the summation formulation is actually more logical. We want to maximize grade, which is 80 plus 10 times 2 multiplied by the choice of studying ML on Saturday morning. If we study ML on Saturday morning, this will be equal to 1, so you essentially add 10 to your grade. Otherwise, this will be equal to 0, so you will be adding 0 to your grade. Similarly, here are the 3 decisions you make about ML on the 3 dates. And here are the 3 decisions you make about OP on the 3 days. Our constraint again is the total grades, have to be less or equal to 100, and that the amount of courses you study on the same day have to be less or equal to 1. This is really the essence of binary programming. You are utilizing binary variables to make a yes or no decision on each one of the courses and the days. So I think it will be easier to see this using the summation formulation, but if you want to formulate this straight in the simple formulation, these are going to be the equation you have to write. So here's your objective, and then you have 5 constraints. Excuse me. The summation formulation actually look a lot simpler. Your maximum grade is simply sum over all courses, so that should technically be there. Your base course grade, as well as the study block time for as well as the decision to study in each block multiplied by the grades you will gain to study in that block, summed over all blocks. What are we doing by summing over all blocks? By summing over all blocks, we are finding the total number of blocks where you studied machine learning, or ML, sorry, no, not machine learning, nobody talking about, there's no machine learning. And this gives you the increment grades you're earning from studying, and this is your base grades, so that gives your total grades. Again, we're maximizing total grades. Your constraints are actually simpler now. You only have to write 2 of them. One is your base grade for every course. So for every course, your base grade plus the grades you gain have to be less or equal to the maximum grade. And that, once again, here's the essence. Summing for every block of time, if we sum over the number of courses you're studying, your total number of decisions have to be less or equal to 1. What does this mean? In English, this says, for every block time you have, the total number of blocks you're studying, so the total number of courses you're studying, has to be less or equal to 1. This, combined with the fact that we're using a 1-0 decision variable, is the reason we can make decisions between things. In this case, we're making decisions between whether we're going to study for ML or OP. If we didn't have this constraint, it's easy to see that we're just going to start putting ones all over the place, because the computer will think, hey, each block of time you spend studying for this course is going to net you an increasing grades. Let's just fill it all up. So whenever you do integer programming, remember this trick. That's it. Really short, huh? As you can see, once you really understand linear programming, everything else kind of just builds upon it. So let's erase these messy marks we have, circle our formulation, and to SAS we go. We already created the data, again, linear problem. Last time we mentioned there are these two things we're not using, and you can see now these are being used in the second problem. So let's go through our formulation once again. First, we create our set course and we read in the course from the data set. We already did that. The next thing we're going to create is the block variables: Saturday morning, Saturday afternoon, and Sunday afternoon. So you can see here that we can also create sets just using string or number notation instead of reading them in. We have our input variables: base, grades per hour. I know I called it grades per hour before here, but technically I'm reading in the value from grades per block. So apologize for that. I'm too lazy to change this. So just assume in this particular problem, grades per hour means the amount of grade you will gain in that course by devoting one block to it. So again, we read our data in there. If you are wondering about the syntax, review the portion from linear programming. Here's the difference. We are creating study blocks denoted by the course and the block, and we're forcing it to be a binary variable. Our objective, again, is maximize grade, which we want to sum over all courses, the value of base course plus the sum plus the grades we will gain from studying. And the grades we will gain from studying is calculated by grades per block times a yes or no decision on whether we're going to study that block, summed over all blocks. Be careful not to put base C inside here, because it's going to add base C multiple times, and I made that mistake and it took me a long time to debug. Again, we have our perfect constraint, which says you cannot go over 100. The base C, so again, for every course, your base grade, adding in the grades you earn from studying, have to be lesser than the course max, which we saw previously is simply 100. And here's that new shiny constraint we added. If we so for every block, or for every study time within the block set, which is Saturday morning, Saturday afternoon, or Sunday afternoon. So technically we're creating three variables here. The number of courses you can study within this one block is at most one. Very easy again. Now we can type in the solve function, solve with mixed integer linear programming, the objective, which is grade, and then pew! We get our results. So the maximum grades we can achieve based on this studying schema is only 180, and we could achieve this by studying for optimization in two of the blocks, and then did I just say optimization? That's not a course we're looking at. Studying for OP in the two of these blocks, and ML in one of the other blocks. In this particular example, this is probably not a unique solution, since you can have one here and two ones here, and you will yield the same value. But as we saw in class, there could be different efficiencies in these blocks, and the value you find will be different then. So that really is integer programming. Again, the trick is your decisions, and often subsequently your constraint or objectives, have to be either integer or binary. And we learned this trick that with binary variables, we can use this type of constraint essentially to force us to choose between one of several decisions. If you want a more detailed example of that, simply look at our homework assignment. We were forced to make a lot of different choices among the promotions, and really we're using the same techniques again and again. So that was mixed integer programming. Again, if you have a good grasp of linear programming, this is a very simple extension. I will be wrapping up this portion here. If you have any questions, please talk to me. I hope you're getting the hang of it. The next thing we're going to look at is Go programming, which, again, a quick overview. It's an extension of linear programming, but this time, instead of trying to maximize or minimize something, you have a specific target you're trying to hit. In our highly fictitious example, we're going to see how we can use Go programming to target certain grades. So back to our linear programming example. You are students, there are 2 exams coming up on Wednesday. You want to decide how long you want to spend studying for each. ML, or OP. You would again get the base grade of 80 ML, 50 OP, and that, as in problem 1, you'll get 2 points per hour spent on ML and 5 points per hour spent on OP. And as usual, you have 16 hours to study over the weekend. You can get over 100 on both. So this entire portion is the same as number 1, so I won't be going over that in detail. And here's the key. You estimated that you need a grade of 85 in both to strike a happy balance between studying all weekend and have some time to yourself. You probably don't need linear programming for this. You can just calculate this out using really basic mathematics, since the two kind of don't interact too much. But we can use this to demonstrate how you will use Go programming to result. So as usual, we set up our sets, does not change at all. Our inputs does not change at all, except for we're adding a new value called the target, which is equal to 85. And our decision variable in this case changes a little bit. So we are deciding, as usual, the hours we want to study for each course over the weekend. But moreover, we're creating a penalty variable, and we're calling that the penalty for over or under studying, i.e. the difference between actual and target grade for course C. Why are we doing this? Well, because we want to essentially minimize the absolute value of actual grade and target grade. And if you remember from your math courses, that is not a linear function. That looks something like this. How do we make it into a linear function? Well, we have one line here and one line here. So we will write actual minus target to be bounded by some penalty, and then target minus actual to be bounded by some penalty. And we want to minimize this penalty so that the absolute values are minimized. That is the only real extension we have to create for this problem. So our objective now is to minimize the sum of the two penalties. And so this is our simple formulation. We write out the penalties here. Again, as we just saw, these two makes it so that you're minimizing actual of ML course and your target. These two make it so that you're minimizing actual OP course and your target. That is the only difference. None of these change. Let's look at our summation formulation. Again, we're trying to minimize penalty, which is simply the sum of the penalty for every single course. And our penalty have to be greater or equal to base plus grades per hour multiplied by hour, subtract target, and at the same time have to be greater or equal to target, subtract the sum of your final grade. This again, we're trying to accomplish minimize actual target for every course. And yada yada yada. This doesn't change from part 1, the linear optimization. This doesn't really change from linear optimization, and this doesn't really change from optimization. That's everything about goal programming. Pretty straightforward, right? Again, the core concept here is we have a goal, and we have some sort of actual value, and we have, again, our goal. And we're trying to minimize the absolute value between actual and target. You want to get as close as possible to that. But in some cases, it might not be. You probably won't be able to hit the target exact. Actually, in most applications, you probably won't be able to do that. We'll see in this case you can, because it's such a simple problem that I just pulled out of POMA. So, as usual, we're going to take our summation formulation to SAS we go. There it is, Go programming. Very, very similar to linear programming. We begin by creating our set, the course, and read it in. We then read in all our inputs. Remember, none of this really changed. We create our total time, and we create the target. So here's the differences between Go programming and linear programming. Instead of simply making decision hours, we're creating a variable called penalty that depends on course. Now, we're not really making explicit decisions on this. It's kind of a product of hours, but since it's still variable, we have to still be calculating it. We have our usual impvar, which is the grades, and we're trying to minimize the sum of all courses, sum over all courses, the penalty. So in this case, it's penalty ML plus penalty OP. And here are the two new constraints. Your penalty for every course we're looking at, your penalty of the course has to be greater or equal to grades minus target, and target minus grades. So again, your penalty has to be greater or equal to the absolute value of grades minus target. And we're trying to minimize that. This is everything that's new with Go programming. We have our penalty constraints, we have our penalty variables, and we're changing our objective function to reflect our goal of minimizing penalty. Everything else stays the same. So let's run. We have happily achieved our target of 85 in both courses, and we achieved this by studying 7 hours LP and 2.5 hours in ML. Well done. Finally, we're going to talk about one last technique that we learned, multiple criteria programming. Really, this is just another extension on linear programming for very indecisive people, and we'll see why. Again, we come back to our simple problem. I don't think I've changed much about this one from the linear example, so let's quickly go through it. We're making decision on OP. We have our base grades, we have our additional grades, our constraint, and max constraint. Now, you decided you want to both maximize grades and minimize study time, and you estimated that you want a minimum of 80 in both courses to be able to sleep at night. But as long as you achieve that, you're really indifferent about grades versus study time, the different combination of grades versus study time. However, while you're different, you want to see what is the Pareto frontier of different grades and study time combination. This is multi-criteria programming. It's for when your client is unsure what he really wants. He wants you to maximize or minimize a whole bunch of different stuff, but at the same time they're kind of conflicting. Now, we know for most problems that given a study time, you could have different combinations of grades outcome. So that there's definitely solutions that are subpar. And our job in this case is to find the solutions that are on the Pareto frontier, aka they're the best solution we can get for a given value of study time or for a given value of grades we're trying to achieve. The setup, as usual, really doesn't change. Excuse me. We begin with our set courses. We do our inputs. We're creating a new variable called course min because we want to achieve a minimum 80 in both courses to be able to sleep at night. Our decision variables, I unfortunately forgot to delete this line, so doesn't matter. All we're deciding is the number of hours to study for a given course. We have, again, our simple formulation, maximize grades, such that your grades have to be lesser than 100, but at the same time, they have to be greater than 80. So here's the new constraint. Your total time has to be lesser than 16, they have to be positive, so these are old. And we're adding in a new objective. We're trying to minimize the total hours. And in summation formulation, we have two objectives, maximizing grade and minimizing study time. Grades calculated by this formula here, and study time calculated by this formula here. And we want our grades to be less or equal to the course max, as usual, but also greater or equal to course min for every single course. So this is new, and this is new. Now, you may be tempted to simply dump this in SAS and run it, but alas, SAS cannot run two conflicting objectives, or probably two same objectives, I don't know. SAS cannot really run the two objectives at the same time. So we're really gonna have to just take one out. But I'll demonstrate how we go about doing that in SAS. So as usual, since nothing really has changed, let's take our formulation and to SAS we go. That is not SAS. Where's my SAS? To SAS we go. Now my code for this is going to be a little long, but you'll see why. Again, we start with proc-op model. Our sets corresponds to our set. Our inputs, again, corresponding to our inputs. Some values we're creating are decision variables and implicit variable calculation. So all of this is, again, similar to exact same, actually, to what we had in the linear programming example. So make sure you understand that one. Now, we have our two constraints, but we're not really going to use this because SAS can only run it one at a time. We have our three constraints where this is a new one. So for every course, our grades have to be greater equal to the minimum grade, which we saw was 80. And let's solve this. So think about how is this current problem different from our initial linear programming problem. Just kidding, I'm not going to pause that long. The only difference, if I solve it right now, is none. There's no difference at all. We're adding a constraint that the grades have to be greater or equal to 80. But as we saw in the first problem, at the optimal solution, this constraint doesn't do anything. So if we run this, we're going to get the exact same solutions that we did in part 1, the linear program. So how is this still multiple criteria programming, you may ask? Well, it's the next step that comes into place. Part 2, almost the same code, one small difference. So we saw if we spend 16 hours, this is our best outcome, 192 for 16 hours. Now, this point is on the Pareto frontier. and it's on the extreme end of study. We can slowly move down our study time from 16 downwards and find every single point on the Pareto frontier. So let's look at this example. Everything is identical except for I'm adding a new constraint that says the total study time has to be, instead of lesser than total time, lesser than 15. So let's run it. Boom, different outcome. You were studying for 15 hours. Here's your Pareto frontier. And again, we can set it to 14 and find a new point on the Pareto frontier and rinse and repeat. Now, the two most important points we want to find are the first one that we already saw. Let's look from the result pane. Are the maximum grades for maximum hours. And now we want to find the minimum point that satisfied our constraint. And this is when we start to utilize that objective we kind of grade out. So again, we have our linear optimization, everything up to this point where we instead of commenting out study time, we're gonna comment out grade, and our new problem becomes minimizing study time. We still want to achieve at least 80 in the course, and run. So make sure when you do this, you're going to have to changing the objectives. If you look above, the objectives grade, the objective here study time, but small differences. What did I just do? I just canceled all my codes. Not really nice. Here's the minimum solution. If you want to study as little as possible and still achieve at least 80 in every course, you're going to put 6 hours in OP and 0 in ML, because in this problem, OP is really simple to solve. I mean, did I say that? OP is much more efficient to study. So what do we see? We see here's the minimum point on our Pareto frontier, and we saw the maximum point on our Pareto frontier and a method for finding every single point in the Pareto frontier. This is multiple criteria programming. So a quick reminder again, in this small video we talk about linear programming in great detail, how to formulate it and how to code it. Then we looked at integer optimization, which really is an extension of linear programming, where your decision constraint and the objective suddenly becomes integer or binary. And then the next thing we looked at was Go programming, which means we have a target we're trying to achieve. And keep in mind, the only addition between this and the other programming is that we're now trying to minimize the absolute difference between the actual value and our target value. And in order to do that, we split it up into two linear constraints. Finally, we came down to multiple criteria programming. Again, this is kind of like running linear programming over and over again, with a subtle difference that you want to try to find the Pareto frontier. And specifically, you want to find the two outermost points on the Pareto frontier, and they will require you to use different objective functions. But once you find them, you can slowly move the constraint on one of them inward and find every single other points on the Pareto frontier. Alright, that wraps up my short, almost, I don't want to say lecture, but little video on optimization, and I really hope this will help you out in the exam to come. Studying for exam? Yes.